Hello everyone, I am Asmina Issa, from University of Clermont-Auvergne in France. I am going to present you INCA system, developed together, with Angela Bonifati from University of Lyon in France, and Farouk Toumani from University of Clermont-Auvergne in France. When exploring and querying inconsistent data, inconsistency measures referring to constraint violations can help the user to quantify the quality of the underlying data and query results. Previous influential work on data cleaning for relational data has focused on detecting and repairing the violations with respect to a set of constraints. Quantifying the level of inconsistency of tuples is crucial for numerous data curation, data science, and machine learning tasks. In this demo and in our previous work, we tackle the problem of inconsistency management from a different angle. We use provenance-informed annotations of the base tuples by building upon Y-provenance and polynomial provenance in order to characterize the level of inconsistency of data and query results. INCA explores stored data inconsistency and query answers inconsistency. INCA implements a 5-steps process. Given a database and a set of denial constraints, INCA uses Y-provenance to identify the inconsistent tuples and then annotates each inconsistent tuple with a monomile expression whose variables record the constraints violated by this tuple. Finally, given a query queue, INCA uses provenance semi-rings to annotate each query answer T with a polynomial expression which encodes how the base tuples used to derive the answer T violate the constraint. Such annotations are then used to quantify the inconsistency degree of each answer. INCA implements 4 measures defined by considering 2 dimensions, query semantics and the quantification method. Please see the companion paper for more technical details about these measures. Consider the following example consisting of an instance of hospital database. It contains data about diagnosis, surgeries, and vaccinations. Also 3 main significant denial constraints on these data are considered. First, we convert each denial constraint into a conjunctive query. The Y-provenance of each of these conjunctive queries is computed and forming the set of inconsistent tuples. For example, the constraint C1 is violated by T2 and T3 together, it is also violated by T2 and T4. So, the tuples T2, T3, and T4 are inconsistent tuples. Then each base tuple in the database is annotated by a monomile consisting by the set of constraints identifiers that it violates. A base tuple that does not violate any constraint is annotated by constant monomile 1 as the tuples T1, T5, T6, and T8. The tuple T2 involves only in the violation of C1 and C2, then it is annotated by C1, C2. Considering the following conjunctive query queue, the polynomial provenance is used to encode the set of constraints violated by an answer. As in this example, we consider only bag semantic. The annotation of each answer is a monomile that shows the only way to derive answer. Answer A1 violates 2 times C1, 2 times C2 and 1 times C3. So the measure value of CBS, that counts the number of time the constraints are violated, for answer A1 is 5. The measure value of CBS for answer A2 is 3 because CBS counts the number of constraints violated. The k best answers, in other words either the k most consistent or the k more inconsistent answers, are computed using TopINC algorithm, that we designed in our previous paper. TopINC works with CBS and CBM, and the challenge behind CBS is the fact that CBS is a non-monotonic scoring function. Example of top 2 answers that are the most consistent answers, either with CBM or CBS measures, are a 4 with inconsistency degrees 0 by CBM and CBS and a 3 with inconsistency degrees 3 and 4 for CBS and CBM respectively. In the following, we illustrate TopINC running on the same example as in the previous slide. This illustration is done only for CBS measure, because the main challenge is with CBS. Also, we need the two first answers the most consistent. Top-INC is level-wise algorithm, as we need the most consistent. Top-INC starts with the level 0, in other words, the level corresponds to the degrees of inconsistency degrees. The array blocks contains, for each relation in join, the set of violated constraints. The cardinality of union of these sets in this array is equal to the level. For the level 0, we have empty set for each relation in join. INCA loads for each relation in join, one by one, tuple that violates set of constraints in blocks array for concerning table. At each read of one tuple in one relation of in join, a test join is done. In this level, one tuple that does not violate any constraint is load for each relation in join. And the join test gives one answer as shown in table res. The only next tuple to read that does not violate any constraint is in the table surgery. So this tuple is added in buffer $HS. A new test join is done but no answer is found. Top-INC moves to level 1 as all tuples of level 0 are read and the top two answers are not computed yet. So, Top-INC add new set of violated constraints. Here the set C1 is add for table S. One tuple that violates C1 is read from the table surgery. A new performing of join is done but no answer is found. For the level 1, Top-INC has only this join test to perform. Top-INC moved to level 2 and read a new tuple to perform the new join test. Top-INC explores all the possibilities in level 2 but not additional answers is found. Top-INC moved to the level 3. One answer is found and the Top-INC algorithm stops running since two first best answers are found. As one can note, Top-INC exploits the attribution of set of violated constraints over tuples as an index. The main computational challenge of a top K algorithm is to determine if a computed answer belongs to the top K or not. In the case of Top-INC, any computed answer belongs to the top K answers. In other words, there is no additional answers computed after a claiming of the top K answers, only the top K answers are computed. We introduce a new class of algorithms called semi-blind algorithms. Considering the number of read tuples on disk, Top-INC is optimal in class of semi-blind algorithms. The INCA system has three main modules: database annotation that performs the pre-processing phase of the database during which each tuple is annotated by the monomile consisting of the set of violated constraints. Also, during this step some utilities function are created in the database. The second module, data profiling, explores input database inconsistency to give some statistic about inconsistency of input data. Precisely, based on the annotations computed at the pre-processing step, it offers a set of tools to extract and aggregate information about inconsistent data. In particular, it encompasses a dashboard which provides insights into various dimensions of data inconsistencies, example percentage of consistent or inconsistent data, distribution of data values in the columns that cause constraints violations, histograms of inconsistent tuples distribution WRT constraints, and so forth. The third module, called query profiling, allows to enable inconsistency-aware query results accounting for most inconsistent or consistent top K and threshold query results. In particular, it provides tools that allow computing query answers together with their associated inconsistency degrees, computing top K answers WRT inconsistency degrees, computing query answers having an inconsistency degree below a given threshold. Now, let's move to the INCA system. For a new database that is not annotated yet, the user has to annotate it first, using the database annotation module of INCA, before loading the dataset for inconsistency profiling. Now, consider adult dataset with the following set of significant denial constraints. We run the pre-processing step of adult dataset. As this step can take more time, we consider only few significant denial constraints applied on adult dataset. The set of constraints are in this format and they are separated by semicolon. Now we can see the set of violated constraints by tuples in adult dataset. So, we have to load first adult dataset. We can see also some statistics about inconsistency in adult dataset with respect to these of denial constraints. This dashboard shows the percentage of tuples in adult dataset that violate at least one constraint among all tuples in adult dataset. It shows also the proportionality of tuples that do not violate any constraints. There are also some other statistics about inconsistency of base tuples in adult that we are described by another dataset. For ease of exposition, we are using an additional database that is already annotated, namely the food inspection dataset containing information about food inspections for restaurants in Chicago. We continue to run the rest of functionalities of INCA with food inspections. We can run these functionalities with adult dataset or any other annotated dataset in a pre-processing step. Let's continue the rest of functionalities of INCA. The Data iProfiling module consists of 3 boards. The dashboard Simple Statistics displays some simple distributions concerning the inconsistency of the input dataset. Precisely, it shows the proportion of inconsistent and consistent tuples. The latter shows the percentage of tuples by number of violated constraints. Only the percentage of tuples that are consistent is not given. For example, consider exactly one constraint violation. 2% of tuples in food inspection dataset violate exactly one constraint. This dashboard also shows the percentage of tuples by a set of constraints that are violated altogether. It shows also the percentage of tuples by constraint. So, 1.73% of tuples violate FC3 and 0.03% of tuples is violate FC3 and FC2. It also allows the user to do some filtering and to enable or disable some of the constraints. For example, let's disable constraints FC2 and FC5 and valid filtering. Then, the proportionality of inconsistent tuples decreases and FC2 and FC5 are not considered in the inconsistency analysis. Through this dashboard, one can also see the description of each constraint in a logical formalism. Let's show the description of constraint FC2. And then, the description of constraint FC1. The dashboard Inconsistency-aware exploration by constraint lets the user dive into the exploration of the inconsistency of the base tuples by constraint. For instance, let us consider FC3 as an example of constraint. The board allows to plot the correlation between FC3 and other constraints of the dataset. For instance, the 3% of the tuples that violate FC3 also violate FC2, while less than 0.1% of the tuples violating FC3 also violate FC4 and so on. Consider constraint FC1, it is not violated by tuples that violate other constraints. It is so separately presented in the figure. This can give main analysis and idea about violation of constraint. Maybe this constraint is inconsistent with the others. If we consider the constraint FC3, INCA can also highlight the set of attributes of the constraint that are the cause of violations. We can select the location attribute to visualize its violated values according to the values of the attribute zip used for grouping. The produced plot allows to visualize for each location value, a stacked bar of its corresponding different zip values and the number of their repetitions. This functionality provides idea about the values that cause the most of the inconsistency. As this figure can displays many values, it can be interesting to limit the set of values displayed using the field limit. Next, let us click on Inconsistency-aware exploration by set of constraints that explores inconsistency by subset of constraints. If we select 2 constraints at a time, this figure illustrates the number of violated constraints for each tuple. The following figure shows the number of violations for each tuple. The dashboard Inconsistency-aware query allows to outline the inconsistency distributions, given a conjunctive query, a measure of inconsistency degrees and a filtering approach, top K, threshold or all answers. For instance, imagine that the user is willing to compute the first 1000 answers of a given query that are the most inconsistent with respect to the CBM measure. This figure shows the distribution of the answers of the given query with respect to their CBM degree. Among the 1000 returned answers, less than 1% have CBM value equal to 2. Then, a second plot in the board shows the distribution of the answers with respect to subsets of constraints violated altogether. In this module, INCA shows also the answers sorted by the value of the given measure of inconsistency. The Query iProfiling module enables also to analyze query outputs with respect to multiple inconsistency measures at a time. In this case, the module provides a synthetic view to summarize the collected information. So, let's select CBM and CBS and rerun the query. This flexibility of selection of measures allows the user to analyze better inconsistency of query answers as shown in the result. In this module, INCA runs query with inconsistency bounded by a value. So, INCA allows the user to show the interval consisting to the min inconsistency degrees and the max inconsistency degrees. This interval is shown to each measure of inconsistency degrees selected. To run a threshold query, user has to give the predicate to filter with the bounded value. For example, if one needs to know answers of query with inconsistency degrees equal to 2, the result is as follows. We can also use all the predicates of inequality. Our code is available on GitHub and one can easily run INCA by following instructions in README file. INCA is implemented in Java with PostgreSQL. It is a web application. We use Spring Boot to do that. It is implemented in consuming light web services developed using Spring Boot. To manage this application and its dependencies, we used Maven. Now, let's show the performance of top-INC algorithm accord to the naive algorithm by experiments. The following figure gives the running time of top-INC and the naive algorithm. As one can note, in the many cases top-INC is the best in running time than the naive algorithm. We have also compared the memory used during computing of the top K answers. top-INC is also the best accord to the naive algorithm. We hope that you enjoyed the INCA system. Thank you.